Okay. So from this lecture on, we're going to start with the domain of rotational mechanics. Okay. So slowly start into rotational mechanics. Rotational mechanics. Okay. So the first thing that I'm going to start. Okay. See, in linear mechanics, what you used to study? Displacement, then velocity, acceleration, and everything was in a straight line, or everything was studied in terms of velocity and acceleration. No, everything was studied in terms of movement. Okay. Now, what happens when I study everything in terms of rotation? Okay, suppose this pen is rotating, okay, or this remote, okay, this remote is said to be rotating, or any object that is said to be rotating. Okay, how do we study those terms? So we'll study those terms in rotational mechanics, and whatever theorems or whatever formulas or whatever things are valid for linear mechanics, the same formulas are valid for rotational mechanics. What I'm trying to say is, see, suppose this object or remote is rotating, okay, then there will be some term to measure the angular velocity. Okay. Now, what does Newton's first law of motion says? A body will continue to move in a straight line. Okay, or a body will continue to move with same velocity until and unless an external force is applied to it. Okay. Same analogy will be applied out here. The body will continue to rotate until and unless an external torque is applied to it. Now, what is torque? So, what I'm trying to say is that rotational mechanics is nothing but the equivalent of linear mechanics out here. Okay. So there are some equivalent terms that you need to study. The first term is, whenever you're learning about mechanics, the first term that you're going to study is angular displacement. Okay. Achha. After displacement, what did we study in mechanics? Velocity. So similar thing out here we study angular velocity. Angular velocity. And after velocity, what did we learn? Acceleration. So out here in rotational mechanics, it would be angular acceleration. Okay. So these are the kinematic terms. Okay. So after kinematics, what did we start with? Dynamics. So what is the first thing that we learned in dynamics? The concept of mass. So the equivalent of mass in rotational mechanics would be moment of inertia. Moment of inertia. Okay. After that, what was there? Momentum. The equivalent of momentum out here would be angular momentum. And what is the equivalent of force? After angular momentum, we learned that something about force, no? The equivalent of force out here would be torque. Okay? Torque. So these are the parameters that we're going to learn in rotational mechanics. Now the basics of this parameter are given in your classes. Okay? I'll just go through the brief. I'll just go through the brief. Okay? Displacement is nothing but whenever suppose this pen is rotating. Okay, about its midpoint. That means if it rotates by 90 degrees, angular displacement is nothing but pi by 2. And whenever you're dealing with the degrees, okay, or whenever you're dealing with angles, in class 11 and 12, it's much advisable to use radians instead of degrees. I've already said that before. Okay. So suppose it's rotated by 90 degrees. So angular displacement is pi by 2. Suppose that displacement was forward in, or that angular displacement was done in 1 second or 2 seconds or delta t amount of time. Angular velocity would be displacement over time. Okay. Similar thing for angular acceleration. Moment of inertia is a little bit of detailed topic that you will learn in your actual classes. But the moment of inertia is nothing but C. Suppose this pen was rotating. Okay. Now it was very heavy kind of pen. Okay. If this pen was very heavy, okay, larger amount of external push, okay, would be required to rotate this pen or would be required to accelerate this pen, isn't it? Similar thing in linear mechanics. If the mass is large, we require much more force to accelerate it, isn't it? So moment of inertia, the equivalent of mass in linear mechanics is the equivalent of moment of inertia in rotational mechanics. Okay. After that, angular momentum, that is the equivalent of linear momentum, and torque is nothing but the equivalent of force. Okay. So in linear mechanics, force was used to change the velocity of an object. Out here, torque will be used to change the angular velocity of an object. Okay. More the force, more will be the acceleration. More the torque, more will be the angular acceleration. And whatever formulas are valid for linear mechanics, or whatever theorems are valid for linear mechanics, same theorem are valid for rotational mechanics. Okay. If angular displacement is theta, angular velocity is d theta by dt. So if linear displacement was x, linear velocity was equal to dx by dt. Similarly, angular velocity would be d theta by dt. Linear acceleration was equal to dv by dt. Out here, angular acceleration would be dw by dt. So let me write the terms to represent angular displacement by theta, angular velocity by omega, angular acceleration by alpha. These are the normal NCERT convention. Okay, moment of inertia by I, angular momentum by L, and torque by tau. Okay, so out here, displacement was a vector quantity, out here also it's a vector quantity. Angular velocity, acceleration was a vector quantity, out here also it's a vector quantity. Mass was a scalar quantity, so out here moment of inertia was also be a scalar quantity. Angular momentum and torque, both vector quantities. Now, one thing to note out here is these kind of vectors are known as axial vectors. What do I mean by axial vectors is, suppose a pen is rotating, it rotated clockwise direction, okay, according to you, or let's say anti-clockwise direction, okay, as you see on the screen. So if you use your right hand, and one more thing that I want to tell you, okay, in your entire physics, you can always use your right hand. Doesn't matter what convention you use. You either use this convention or this convention, right hand finger rule, or palm convention. Doesn't matter what convention you use, as long as you use your right hand, it doesn't make a difference. Okay. So suppose it is rotating in this direction. Okay. If you move your palm, okay, or if you curl your finger in the direction of your rotation, the thumb is the direction of vector quantity. That means if the pen is rotating in this direction, okay, that means displacement vector would be towards me. These kind of vectors are called axial vectors. But the vector is out of the plane of rotation or angular velocity or angular acceleration or what. Understood this much? Okay. And whatever formulas are valid for linear mechanics, same formulas are valid for rotational mechanics. That means velocity is equal to dv by dt, out here angular velocity is equal to d square by dt. Acceleration was equal to dv by dt, out here angular acceleration would be d omega by dt. Okay. And force was equal to mass and into acceleration, out here torque would be equal to moment of inertia into angular acceleration. Angular momentum is equal to mass into velocity. Okay, sorry, momentum was equal to mass into velocity. Angular momentum would be equal to moment of inertia into angular velocity. So whatever formulas were valid for linear mechanics, same analogical formulas will be valid for rotational mechanics. Okay, so this one should be understood up to now. Fair and fine. Now there are few specific relation between linear mechanics and rotational mechanics. Okay, so we'll go through that topic. Relation between linear mechanics and rotational mechanics. Rotational mechanics. Okay, relation between linear mechanics and rotational mechanics. Now let's say a circle is there. The body is moving in a circular path. Okay, there's a body out here. Okay, this body is moving in a circular path. In this circle, okay, this body is rotating somewhat like this. Okay, now let's say this is the center of the circle. This is the radius of the circle. Okay, okay, and it's rotating in this direction. This direction. Okay. My first question is, suppose in time t, okay, in 1 second or 2 seconds or whatever is the time, delta t, okay, suppose in 1 second it reached out here, okay, okay, that means displacement is in this direction, okay, and velocity is also in this direction, okay, and if this particle started from rest or was changing the velocity, depends upon the direction of change of velocity, but let's say the particle started from rest, okay, and it went out here, okay, that means acceleration is also in this direction, no? Or the tangential acceleration is in this direction. Tangential acceleration is also in this direction. Okay. My question out here is this particle, okay, moving this direction in delta t. Now, if I analyze this motion in terms of rotation, okay, out here this particle rotated by, let's say, theta degrees. Okay, let's say this is theta degree for delta time t. Okay, theta degree. My question out here is, what is the relation between theta, r, and s? Okay, what are the relation between these variable quantities? So that is the thing that we are going to study out. Okay, the first quantity that we are going to study is what? Angular displacement. So angular displacement. Angular displacement given by theta. Okay, it is given that displacement vector or linear displacement vector, that means this much distance, okay, linear displacement vector is equals to theta cross r. Okay, and whenever you are using vector product or vector cross product, you can always use your right hand three finger. Okay, make your right hand in this orientation. Okay, this should be the first vector, this is the second vector, this is the resultant vector. If you notice properly, each of the fingers are perpendicular to the remaining two. That means this finger is perpendicular to these two fingers, this finger is perpendicular to these two fingers, and this finger is perpendicular to these two fingers. Okay, not get stupid ideas, just focus on the topic. Okay, what I'm trying to say is, whenever there is cross product, okay, you can always, not you can always, you have to always use your right hand. Okay, in your entire physics, whenever any types of cross product, okay, or any chapters, you always use your right hand. Doesn't matter you curl your finger or use the palm rule or use this finger, as long as you use your right hand, everything is correct. Okay, now suppose I'm trying to find out the displacement, the relation between displacement and r. Okay, what the first thing that I said to you is, always use your right hand. Okay, this is the first vector, second vector, resultant vector. One second, first vector, second vector, resultant vector, like German counting. first vector, second vector, second vector. Okay. Now let's see how I reduce this formula from this flipping the room. Acha. A's vector is equals to theta vector into r vector. If the body is rotating in this direction, okay, I'm still using my right hand. What is the direction of theta vector? The theta vector is in this direction, isn't it? Theta vector is in this direction. Okay. And I'm telling you that AC is equals to theta cross r. So first vector is theta, second vector is r, then resultant AC is nothing but in upward direction. See, AC is in upward direction. Similarly, if it rotated theta degree in say 2 seconds, or the angular velocity out here is given as omega, 2 radians per second or 1 radians per second or whatever. If it is rotating in this direction, even the angular velocity vector will be in this direction. Okay. So the second term that we are going to study is angular velocity. Angular velocity given by omega. Similarly, like displacement, linear velocity is equals to angular velocity cross r. Okay, understood this much? Yeah. And one more thing that you need to note out here is sin theta is equals to s cross r. Suppose large displacement occurs. Large displacement is suppose final position. This is initial position. Okay, theta is equals to 90 degree. Fine, 90 degree means pi by 2. Okay, this is the final position. This is the initial position. You might have a confusion that displacement is a straight line connecting between this point and this point. No, so this would be the displacement vector. Okay, so a should be equals to theta cross r. Out here that doesn't happen. Okay, out here whenever you're multiplying theta into r, you get the length of r. That means if you multiply pi by 2 into r, you'll get this length instead of the line connecting final position and initial position. Understood? Okay, so note out here for large displacement, L is equals to, or let's say this is the value of s. Okay, s is equals to theta into r. S is equals to theta into r. Okay, that means you are not applying, you are applying cos product. See, what actually is happening out here is this theta out here is very small, and when you keep on integrating this s over this large theta, what happens is you get the length of entire path instead of a straight line connecting final position and initial position. Understood? So s is equals to theta into r, where s is the length of path traveled by the body. Okay, understood this much? Similarly, if the body was accelerating in this direction, okay, angular acceleration, the third parameter that you're going to study, angular acceleration, alpha. Acceleration is equals to, what is the formula? Acceleration is equals to alpha cross r, the same kind of formula. Okay. And one more thing to note out here is in circular motion, you studied that if this body is rotating in a circle or moving in a circle, there are two kinds of acceleration. The first one is the tangential and the second one is the centripetal. So out here, if I say linear acceleration is equals to alpha cross r, what is the acceleration that I use out here? What is the part of linear acceleration that I use out here? Is it the centripetal acceleration, or is it the tangential acceleration, or is it total acceleration? Which acceleration do you use out here? The acceleration that I use out here is nothing but the tangential acceleration. We do not use the centripetal component of acceleration in this formula. So tangential acceleration is equals to alpha cross r. Okay. So the first thing I said is linear term is equals to angular term cross r. Okay. See out here, linear term is equals to angular term cross r. Okay. And two things to note out here is for large displacement, s or linear or the angular displacement or the linear displacement that I calculated by theta into r is nothing but the length of path, not the final, or not a straight line connecting between final position and initial position. Understood? And the second thing to note out here is when I say acceleration is equals to alpha cross r, that means tangential acceleration is equals to alpha cross r. Okay. So the shortcut method of remembering this is nothing but linear component is equals to angular component cross r. And whenever you are using vector product, you always use right hand 3 finger rule. Okay. Now this shortcut of remembering, that means linear component is equals to angular component cross r, is valid only for kinematic terms. That means if you observe out here, there is no component of mass or there is no dynamic term out here. No, there is no momentum, there is no mass kind of thing. Okay, so these are kinematic terms. Kinematic terms. So the second question I have is, sir, how are dynamic terms related, or what happens for dynamic terms? Okay, so we'll go on to the dynamic terms. So the first dynamic term that we learn is moment of inertia or equivalent of mass. Moment of inertia given by I. And how is I related to mass? I is nothing but m r square. Okay, m into r square. Understood? I is equals to m r square. Now, moment of inertia of various objects will be discussed detailed in your syllabus out here. I'm just showing you the moment of inertia of this small particle revolving around this circle. Okay, the moment of inertia about this axis of rotation means this one. Okay, or about this point. Okay, there will be some confusion and a very good concept between axis of rotation and point of rotations. Okay, and that I'll do at the end of this, not end of this lecture, end of the questions of period. Okay, so that we understand very clearly. If I do it right now, we'll get confused, very confused. Okay, but that is an important aspect that is very important from your JW perspective. There's a question from 2016 also. If you know the relation between point of rotation and axis of rotation, or how are they related, or what happens, okay, same question becomes very easy. And this is mostly skipped every year. Okay, so right now forget about the relation between point of rotation and axis of rotation. Right now just focus the moment of inertia of this particle about this center point. Okay, I'm just using wrong analogy, center point. Moment of inertia is defined about an axis, but let's say about this point. Okay, the moment of inertia is nothing but mass of this object or mass of this particle into r square. Okay, or distance of this particle from the point of rotation or axis of rotation. Okay, so if this particle has a mass m, moment of inertia of this particle is nothing but mass into r square or r square. Okay, now there are various moment of inertia of various shapes and sizes through different axes of rotation that will learn in your rotational mechanics, and that will learn on later part of the classes also. Okay, it's not like I'll skip it, but for now just focus for a point rotating about a circle. Okay, all I'm trying to do in this class is give you a relation between linear terms and angular terms, nothing more, nothing less. Okay, let's just go through that portion. Okay, fair and fine. Now as soon as we introduce mass, okay, the next portion would be momentum. So out here, angular momentum, okay, given by L. See, angular momentum. Now out here, angular momentum is equals to R cross linear momentum. Okay, R cross linear momentum. The first thing, the angular momentum of this particle about this point of rotation, point or axis of rotation, okay, at this point of rotation, okay, is how much? R, okay, first vector R, and what is the direction of linear momentum? Mass into velocity, this one. So the direction of angular momentum would be same as the direction of angular velocity. Let's see, R cross P. The direction of angular momentum is this one. The direction of angular momentum would be same as the direction of angular velocity. Okay. Now the last term that we're going to study is torque, given by T. Okay, torque is equals to R cross F. That means if this particle, okay, was being pushed by some force, okay, the torque about center of rotation or the torque about center of rotation would be nothing but R cross F. Okay, so the torque vector would be towards, the torque vector would be in this direction. Okay, so these are the 6 terms that you need to learn. One more thing, in kinematic terms, okay, the easier way to remember was linear terms is equals to rotational terms cos R. See, that changes for dynamic terms. See out here what happens, rotational term is equals to R cross linear terms. Okay, so for dynamic terms, the formula or the way of remembering things changes. But angular term is equals to R cross linear term. Understood? So these are nothing but dynamic terms. Dynamic terms. Now what are the 2 things that I said out here? Okay, whatever formulas are valid for linear mechanics, the same formulas or same equivalent formulas are valid for rotational mechanics. If velocity is equals to dx by dt, out here angular velocity would be equals to d theta by dt. If acceleration is equals to dv by dt, out here angular acceleration would be dv by dt. Okay, out there if momentum is equals to m into v, out here angular momentum is equals to I into omega. If out there force is equals to mass into acceleration, out here torque would be equals to moment of inertia into angular acceleration. Okay, so whatever formulas are valid out there, the same formulas are valid out there. Okay, so having learned these 2 situations, we'll go through some questions of irodov. Okay, and then again we'll come back to the theory of rotational mechanics. Okay, so let's go to the first question. Okay, see, as I said, okay, the language of irodov is used nowhere in your JW syllabus, but the concept of irodov is very important or more than important for your JW exam. Okay, so out here, what I'm trying to say is you understand the angular momentum of a particle related to a certain point O varies as time as m is equals to a plus bt square. So out here, this is nothing but angular momentum. Okay, this is angular momentum. Out here, this is a vector, e vector. But a and v are constant vectors, and a is perpendicular to v. Remember this point. Okay, a is perpendicular to v. This will be very helpful in our calculation. Okay, find the force moment. Force moment is nothing but torque. Okay, so do not bother about the language of irodov. Language of irodov is not important from a JW perspective. However, the concept that I'm using in this question is much more important. Okay, in your actual exam or in your JW exam, they'll always use torque, tau, or angular momentum L. They won't be using languages of irodov or any other calculus-based language. Okay, the force moment, torque, tau. Force moment is nothing but torque out here. Okay, relative to point O, when particle angle between vectors n is nothing but vectors L, angular momentum and torque. equals 45 degree. Okay. Let's go to this question or let's go to this situation also. Okay. So in this relation, if you notice one thing, see torque, angular momentum, then time means angular acceleration, omega, theta. Okay. If you notice all these terms are valid about a point. Okay. That means I'm considering this as the center and then omega is equals to this or this. Then angular acceleration is equals to this or this. So whenever any body is rotating, okay, all your parameters are valid through a point of rotation. Okay, that means out here my point of rotation is nothing but the center of the circle. Okay, so see in linear mechanics, whenever I used to study displacement or velocity or acceleration or momentum or force or anything, we used to consider an origin. No, there was an origin, and about origin, what is the position vector? Then final position minus initial position was equal to displacement vector. So there was an origin, isn't it? Similarly, out here, origin is nothing but the point of rotation. Okay, so every rotation is defined about a point. Understood? Now let's go to the question. In this question, what is being said is that angular momentum is given by a vector plus b vector t square. Okay, or the equation of angular momentum in terms of t is given by a vector plus b vector t square. Okay, and while a vector is perpendicular to b vector, find the torque. Okay, relative to point O. That means point O is nothing but the origin. Okay, point O acting on the particle when the angle between angular momentum and torque is equals to 45 degree. So in this question, can I simply just way to look at this question is simply change the variable. Simply change the variable means if I read this question somewhat like this, okay, the linear momentum of a particle related to a certain origin varies as time as momentum is equals to a plus bt square, where a and b are constant vectors with a perpendicular to b. Find the force relative to the origin of the particle when the angle between momentum vector and force vector is equals to 45 degree. Okay, now can you solve it? Now the question becomes much easier. Okay, it is said that the equation of momentum is given by this one. Okay, I need to find out the value of torque. Okay, when the angle between momentum vector and force vector or equivalent of torque vector is equals to 45 degree. That is the question out here. So suppose if the equation of momentum is given, okay, or the equation of linear momentum is given, how do I derive force from it? If momentum is given, force is nothing but dp by dt. So similarly, if angular momentum is given, how do I derive torque from it? Torque is nothing but dl by dt, or rate of change of angular momentum. Whatever formulas are valid for linear mechanics, the same formulas are valid for rotational mechanics. In linear mechanics, force was equals to dp by dt. In angular mechanics, it would be dl by dt. Okay, so torque is equals to dl by dt. Fair and fine. So torque vector is equals to, if I differentiate this term, a plus bt square. Okay, with respect to t, what do I get? 2bt. Fair and fine. See, 2bt. Okay. Now the question is saying find the value of torque. Okay, when the angle between L vector and tau vector is equals to 45 degree. So whenever angle between vectors are given, what is the first intuition that you get? The first intuition is somehow we have to use cross product, isn't it? So can I say L cross T, L dot tau is equals to magnitude of L into magnitude of tau into cos theta. Theta is the angle between L vector and tau vector, isn't it? And out here theta is given by 45. So cos 45 is nothing but 1 by root 2. Fair and fine. Now what is the value of L vector? L vector is given by a plus bt square. Okay, what is the value of tau? The value of tau that we achieved out here is nothing but 2bt. 2bt. 2bt square. And if I multiply it, okay, or if I cross product it, it would be nothing but a vector into 2bt square plus bt square into 2bt square, isn't it? L vector is nothing but this one, tau vector is nothing but this one. And when you multiply these two terms, you get these two terms. Okay. Now, the important thing in the question that is given out here is A is perpendicular to T. Okay, that means what? X axis is perpendicular to Y axis. Okay, now see, whenever you dot product A dot B, suppose you multiply A dot B out here. Okay, A dot B, the angle between A and B is 90 degree, no? And cos 90 is nothing but 0. So this entire term becomes 0 out here. No? This entire term will be equals to 0. Why? Because A is perpendicular to B. Similarly out here, the angle between B and B is nothing but 0. Cos of 0 is nothing but 1. And whenever you are multiplying dot product, it becomes a scalar quantity. So this quantity would be nothing but b square or 2b square t to the power 4, or is equals to 2b square, or b dot b is nothing but b square and t to the power 4. Okay, so this entire term or this L dot j, this L dot j would become 2b square t to the power 4. Okay, this term. This much should be understood. Now see, we need to find out the magnitude of L vector. Magnitude of any vector, suppose ai plus bj. okay, is given. What is the magnitude of, suppose, any vector A vector or any P vector is given. Okay, P vector is equals to AI plus Bj. What is the magnitude of P vector? Magnitude of P vector is nothing but A square plus B square under root. And why was that? That was because I, the direction of I vector, is perpendicular to the direction of J vector, no? Isn't it? So similarly, if a vector is given, okay, A vector plus B into P square, and A is perpendicular to P, what is the magnitude of this vector? The magnitude of this vector is nothing but A square plus BT whole square under root, isn't it? Suppose in linear mechanics, okay, any vector was given by A T cube I plus B T cube J. Okay, what, this was linear mechanics, this was a vector. What is the magnitude of this P vector? Magnitude of this P vector was nothing but this vector square plus this vector square under root. Okay, now instead of giving you I and J in irodov, they explain that A vector is perpendicular to B vector, or A and B are constant, or A vector is perpendicular to B vector. The same thing, or will obtain the same magnitude, no? Instead of giving I and J, they explain this term. A and B are constant, but A is perpendicular to B. So if I have to find out the magnitude of this vector, it would be same thing, no? So out here, the term would be out here, or the magnitude of this term would be nothing but L vector is nothing but under root of A square plus BT square whole square. Okay, and the magnitude of tau term would be nothing but 2BT whole square under root. Why? Because it doesn't have any other component. Okay, and if I remove this whole square under root, 2BT square whole square under root. Okay, 2BT square whole square under root. Okay, now if I copy this entire equation out here, what do we get? L dot tau. L dot tau is nothing but 2B square T to the power 4. L dot tau is nothing but 2B square T to the power 4 is equals to magnitude of L, A square plus B square T to the power 4 into magnitude of tau is nothing but 2BT square into cos theta or cos 45 or 1 by root 2. Now let's simplify the equation. T square, it becomes T square. Okay, B square gets cancelled, 2 and 2 gets cancelled. Let's simplify it a little bit. It becomes T square, then out here this entire term will get cancelled. If I bring this root 2, out here, it will become root 2 BT square. So I'm bringing this root 2 out here. Okay, now I get this equation. Now if I square left hand side and right hand side, okay, left hand side whole square is equals to right hand side whole square. What do I get? I get 2B square T to the power 4 is equals to A square plus B square T to the power 4. Then fine. Now 2B square T to the power 4, and out here is B square T to the power 4. If I bring it to the left hand side, it will be 2B square T to the power 4 minus B square T to the power 4. So it gets something around B square T to the power 4 is equals to A square. Or if I isolate the value of T is equals to under root of A by B. So T is under root of A by B. That means what is happening out here? Or what did we obtain out here in this equation? See, in this equation we obtain that when the angle between torque vector and angular momentum vector, or when the angle between these two vectors is equals to 45 degree. Okay, when the angle between these two vectors is equals to 45 degree, that happens at time t is equals to under root of A by B. That means when time t is equals to under root of A by B, the angle between angular momentum vector and torque vector is equals to 45 degree. Now what is the question asking? The question is asking find out the value of torque. So we already obtained torque is equals to 2BT. So from this equation, torque is equals to 2BT, or 2B vector into what is the time when torque vector is perpendicular to, or not perpendicular, 45 degree to angular momentum vector is nothing but under root of A by B. So 2B into under root of A by B. So this was the first question from rotational mechanics. Okay. So in this question, this was nothing but the concept of linear mechanics translated to rotational mechanics. If you just translate the question, okay, instead of using angular, you use linear terms. Okay, the momentum, linear momentum of a particle relative to the origin varies as A plus BT square, where A and B are constant. Okay, A is perpendicular to B. Find the force relative to the origin when the angle between force vector and momentum vector is equal to 45. The same question is after, just in rotational terms. Okay. So now we go to this next question. Okay. In this next question, what is being said is that there is a projectile motion happening. Okay. A ball is thrown with an initial velocity of u naught. See, initial velocity of, let's say this is v naught, okay, instead of u naught. Find the time dependence of the magnitude of the ball of angular momentum relative to the point in which the ball is thrown. Find the angular momentum at the highest point. Okay, so out here this ball is thrown at an angle alpha with the horizontal. Okay, this is a projectile motion in which a ball is thrown at an angle, means at an angle alpha with the horizontal. So how will the ball go? The ball will follow this path, isn't it? Okay. The question out here simply states that at any point in the path, okay, at any point in the path, find the angular momentum of the ball or of the particle about the point of projection, or consider this as origin Okay, then find out the angular momentum of the ball when it goes out here, or find the angular momentum of the ball when it goes out here, or find the angular momentum of the ball when it goes out here. And angular momentum about this origin or about this point. What did I say before? Whenever you are considering angular momentum, or whenever you are saying anything about angular momentum, torque, or angular velocity, angular acceleration, displacement, this R, there is an R vector, no? And what does this R vector signify? That means there is an origin, isn't it? And that origin is called point out here. Understood this much? Okay. So I have to find out the angular momentum of the particle at any point. Okay, at any point during the projectile motion about the origin, and the origin is said to be the point of projection. This much is understood. And this question has two parts. The first part is I have to find out the angular momentum about any point in the origin. Okay, sorry, at any point about the path. Okay. The second part of the question is I have to find out the angular momentum when the path or when the ball or when the particle is at the topmost position. Okay, at the topmost position of the projectile. So to understand this question better, okay, first I'll solve part 2 of the question and then I'll move on to part 1 of the question. So part 2 of the question is saying, let's deal with part 2 of the question first. Okay, part 2 of the question. See, part 2. So part 2 of the question is saying, this is a ball that is being projected from out here. The path of the projectile will be somewhat like this. The initial velocity v0 at an angle alpha. I have to find out the momentum or angular momentum of the particle when the ball is at topmost position or when the ball is out here. I have to find out the angular momentum about this point. What is the formula for angular momentum? AL is equals to how much? AL is equals to R cross P. See out here. AL is equals to R cross P, isn't it? AL is equals to R cross P. So AL is equals to R cross P. Okay, R cross P. Okay, just wait a minute, okay? L is equals to R cross P, where P is nothing but the linear momentum, and linear momentum is nothing but mass into velocity. So L can be written as mass into R cross V. Why? Because P is nothing but mass into velocity, and that mass I have taken outside. That's common. Because mass is a scalar quantity, I can take it common. Now we need two terms. The first term is R, the second term is V. Okay. So what is the velocity at topmost point? The velocity at topmost point is nothing but V cos alpha, or V naught cos alpha. Okay. My second question is, what is the value of R? The value of R is nothing but this distance, no? This distance. So this is the value of R. So if I say it properly, this is the value of R. Okay, this is R vector. Now when I say L is equals to M into R cross V, that means what? L is equals to M into magnitude of R into magnitude of V into sine theta. But theta is the angle between R and V, isn't it? R cross V is nothing but R magnitude of R into magnitude of V into sine theta. But theta is the angle between R and V. And if you see the direction of L vector, what happens is the L vector is nothing but you always use your right hand three finger rule, isn't it? That means the L vector will always be in or out of the plane of paper or perpendicular to both the vectors. That means if two vectors are there, you have to make a plane in that two vectors, and the resultant vector is along the direction or perpendicular to plane of both the vectors. Okay. Now see, I have to find out the angle theta, but angle theta is nothing but the angle between R vector and E vector. Okay. But instead of finding the angle theta, just hear me. Okay. I'm rearranging this term. This term. M R V sin theta. I'm writing this term as M into V into R sin theta. Okay. So this L is nothing but M into V into R sin theta. Okay. Now if you see properly, okay, if this angle is theta, and if I draw a straight line out here, okay, I'm drawing a straight line out here, then this angle is also theta, isn't it? If this angle is theta, this angle is also theta. Now if I draw a perpendicular line out here to the horizontal, this is all but 90 minus theta. This angle is nothing but 90 minus theta. So if I want to say R sin theta is nothing but this much length, no, or the length of maximum height. So this much length is nothing but R sin theta. So this much length is nothing but R sin theta. So I can easily write angular momentum at maximum height is equals to mass into velocity at maximum height, V naught cos alpha, into R sin theta. R sin theta is nothing but maximum height, okay, into H max, where H max is nothing but, you know, from projectile motion, U square sin square theta by, U square sin square alpha by 2g. So mu naught square sine square alpha by 2g. Okay, so if I rearrange the term or angular momentum at maximum or at topmost position is equals to m into mu naught cos alpha, initial velocity into cos alpha into mu naught square sine square alpha by 2g. Okay, so you can either rearrange this term or leave this term as it is. Doesn't make a difference. Okay, so what I did out here is I simply did r cross v. Okay, the r cross v I simply did out here. There was an angle between r and v, and what did I take? I took r sine theta into velocity. Okay, and whenever you're taking dot product, no, sorry, cross product. See, in dot product, you used to take the component along the vector. Okay, in cross product, what you simply have to do is take the component perpendicular to the vector. Okay, we'll understand more of these as we begin to solve the relation between torque and force and similar kind of things. Okay, but a general rule to remember is in cos or in dot product, okay, or whenever you're taking cos theta, you have to take along the vector. Okay, in sine theta, you have to take perpendicular to the vector. That means what I did out here is I simply drew the first vector or second vector. This was the second vector. Okay, I drew a line perpendicular to the second vector and took the component of r along that perpendicular line. Okay, now there is another way of solving the same question. You can take a line perpendicular to the r vector, okay, and take the component of velocity along that perpendicular line. It will give you the same answer. Okay, understood? Suppose instead of what I'm trying to say is instead of VR sin theta, suppose it was VR cos theta. Just assume it was VR cos theta. What you used to do? You used to either take R cos theta or V cos means theta. Both have the same value, no? Similarly, out here, whenever sine is mentioned, okay, just draw a perpendicular to the first vector, okay, and take the component of second vector along that perpendicular line, or draw a perpendicular to the second vector and take component of first vector along that perpendicular line. Okay, that is simply nothing but cross product. Understood that thing? Okay. Now we move on to the second part of the problem. Okay. The second part of the problem, also not the second part of the problem, the first part of the problem. Okay. The first part of the problem is saying that, see, the particle flew from outlet to outlet in a projectile motion. Okay. At any point in the path, okay, at any point in the path, I have to find the angular momentum of the particle about the origin. And where is the origin? The origin is about point of projection. Okay. That means suppose that at time t, the particle is out here. Okay. I have to find the angular momentum of the particle, okay, about this point, okay, or about origin, and the origin is at point of projection. Okay, so how do I solve part 2 of the question? See, we know that angular momentum is equals to r cross p, or mass into r cross p, or position vector cross momentum, position vector cross velocity vector. Okay, so the variable, see, at different time the particle will be at different positions, no? Okay, so let's say at time t, I have to find out the position of the particle. Let's say the particle was out here at time t, isn't it? The velocity would be in this direction. This is the velocity vector. And what is the r vector? The r vector is nothing but the straight line connecting this position and this position. Okay. The r vector is nothing but a line connecting origin and the particle. This is r vector. Okay. Now I do know that r cross v will give us the angular momentum. Fair and fine. So how do I find out r cross v? See, whenever acceleration is constant, there are three formulas that I can apply. V is equals to u plus at, s is equals to u plus half at square, and v square is equals to u square plus 2as. Okay. So let's apply the first formula. V vector is equals to u vector plus a vector into t vector. Okay. This is the first formula. So now pay attention out here. While dealing with kinematics, okay, 1D or 2D motion, what I have to do with, I have to break this formula into x component or y component, and then I have to solve, isn't it? X component of velocity is equals to x component of initial velocity plus x component of acceleration into time, and y component of velocity is equals to y component of initial velocity plus y component of acceleration into time. But you can also use this formula in vector terms or directly in vector terms. That means velocity vector x plus y component is equals to initial velocity vector x plus y component plus acceleration x plus y component into time. But while adding this in terms of velocity vectors, just make sure you are using vectors law of addition. Okay, not scalar law of addition or scalar law of not scalar addition. See, what used to happen is whenever I used to break this equation into x component to y component, what used to happen is, see, x component of velocity is equals to x component of initial velocity plus x component of acceleration into time. So what is the angle between this u and this a in x component? 0. So the entire equation is to become resultant is equals to a plus b. And if velocity and acceleration is in opposite direction, cos of 180 was -1. So a square plus b square minus 2ab would become a minus b whole square. So this and this would get subtracted. Understood? But what I'm trying to say is that this is essentially but a vector equation. Okay, this equation out here is nothing but a vector equation, and I can solve this equation as a vector quantity itself. Clear and fine. So we got the velocity v. That means my method of obtaining this velocity v is from this equation. Okay, how do I obtain the value of r? The value of r is obtained by equation s is equals to ut plus half at square, where s, u, and a are vector quantities, t is scalar quantity. The s out here, okay, the s out here is nothing but the r or the position vector at time t from the origin. Okay, so instead of s, I'll write down r. This much is understood. Okay, so I got the value of v, I got the value of r. Now simply substitute these values out here and out here. Okay, so before substituting, I must find the value of v. V vector is equals to what was initial velocity vector? Initial velocity vector was nothing but v naught, or v naught out here. See, v naught plus v naught vector plus g vector into t. T is a scalar quantity. Out here it would be r vector is equals to initial velocity vector v naught into t plus half g vector into t square. Okay, so if I substitute these two terms v and r, okay, I'm substituting v and r out here. Okay, so angular momentum is nothing but m into r cross b. Okay, what is the value of r? The value of r is nothing but mu naught t plus half gt square. So the value of r, let me write down the bracket. Okay, the value of r is nothing but mu naught t plus half gt square, where mu naught and g are vector quantities. Cross, okay, v is nothing but v naught plus gt. V naught plus gt. Okay, so this is my angular momentum vector in instant. Okay, now you have done vector multiplication. You used to do a cross b, you used to do I cap, j cap, k cap, then ai plus bj plus ck, then second vector terms, and used to solve the determinant. No? Okay, there is one more shortcut method. See, you can do it by that way also. Okay, the problem out here is the vectors are not defined by I and j. Okay, so it will be a little difficult. But the method that I'm showing you out here, that's one more thing. This mu naught and g are vector quantities. The method I'm showing you out here, okay, can be applied for any terms. That means you can do it if the vector is given in terms of I, j, and k. You can do it if the vector is given in terms of directly this term. Okay, and what is the method? See, can I simply say this as a plus b into c plus d? Just basic multiplication. Okay, algebraic multiplication. A plus b is equals a plus b into c plus d. So if I apply basic algebra, okay, the term would be a into c plus a into d, okay, plus b into c plus b into d. We'll do the same thing out here. Okay, so L is equals to M. Now observe properly. Okay, a into c. See, in vector cross product, you can never interchange the variables. That means a cross b is not equals to b cross c. So make sure you remember the order of the variables. Okay, do not interchange the order of the variables. Understood? This is the first thing you must be careful while multiplying by this method. Okay, so it will be mu naught t cross mu naught into, so it will be mu naught t cross v naught, sorry, v naught t cross v naught. Okay, a into c plus a into d. Okay, so it will be v naught t cross g into t. Okay, fair and fine. Now b into c plus half g vector t square cross v naught. Okay, plus half gt square cross gt. Vectors. Understood? So I got this term. Okay. Now the first thing, see, there are two kinds of vector variables, mu naught or v naught and g. Okay. So my basic intuition is what is the angle between v naught and g. So what is the angle between initial velocity vector and g vector? See, if initial velocity vector was making an angle alpha with the horizontal and g vector is always downward. Okay. What is the angle between v naught and g? What is the angle between v naught and g? The angle between v naught and g is nothing but 90 plus alpha. Understood? So remember this, the angle between g and v naught is 90 plus alpha, and this point would be very useful in solving this multiplication. Let's see, okay, let me multiply. Or L is equals to m into, now let's take this first term, okay, v naught t cross v naught. Okay, whenever I'm doing vector multiplication, okay, a cross b, what is the resultant? magnitude of A into magnitude of B into sine theta, isn't it? So what is the angle between this V naught and this V naught? 0. Both are the same vectors, So magnitude of this into sine of 0. So sine of 0 becomes 0. So this entire term becomes 0. Understood? This entire term will become 0. Similarly, see this term, okay? Half gt square into or cross gt. The angle between g and g is 0. So similar way, this term would also be 0. Okay? Now in vector multiplication, you must understand that the resultant is also a vector quantity. That means A cross B. Suppose A cross B is equals to C. That means C is also a vector quantity. And that C vector is perpendicular to both the vectors A and B. That means what? If there are two vectors, first vector, second vector, the resultant vector would be perpendicular to the first both vectors. Okay? Or the resultant vector would be perpendicular to the plane of first two vectors. And till you use your right hand, everything is fair and fine. Okay? Now what I'm trying to say is, if the vectors, okay, or are perpendicular to the plane of first two vectors. That means the resultant vector is perpendicular to the plane of first two vectors. It can be upward also, it can be downward also. This is the first vector, this is the second vector, and this is the plane of vector. So my resultant vector can be upward also, my resultant vector can be downward also. How did I determine which angle is it? Till you use your right hand, everything is fair and fine. Okay. Now let's see this term. Okay. V naught into cross G or V naught cross G. Okay. If I take my hand, right hand, okay, point my four fingers towards V naught and then curl it towards G. My thumb gives the direction of this direction. Okay. So this direction is the resultant of these two terms. Okay. Now G cross V naught. If I take my four fingers downward, okay, and curl it towards V naught, my thumb is the direction of this direction. So this direction is the resultant of these two product. Okay. Now I must quantify this direction and this direction. No. So the plane of paper is in x direction and y direction. Can I say this direction to be z direction? So if one of the direction is positive, the other direction is negative. Okay. So which direction is positive, which direction is negative? It doesn't matter in this question. But a basic rule of thumb is, see, if your x direction is in this direction, y direction is upward, z direction would be towards z. That means you can use your right hand. And why is that? Because I cap cross j cap is equals to positive k cap. Understood? So x axis, y axis, z axis, or positive of z axis. So the other direction would be the negative of z axis. So this value or this product, okay, this product has a value in this direction. So if I say, let me just clean up this term, okay. So magnitude of V, so I can write V naught cross T is equals to V naught cross T into GT is equals to magnitude of V naught T into magnitude of GT into sine of angle between V naught and G. Okay, and the vector is in this direction or minus k. Let's say this direction is minus k. Okay, in this question it doesn't matter. Okay, but if x axis and y axis are specified, you have to take or you have to use the right hand rule. Understood? Now let's take this term. This term is nothing but magnitude of this vector into magnitude of this vector into sine of angle between these two vectors. So plus half gt square into v naught. Okay, half gt square into v naught into sine of angle between first vector and second vector. Okay, and the direction of this vector is in this direction. Understood? You can also use the right hand three finger rule. See, first vector, see, while using these vectors, okay, v naught cross g. Okay, so if you take v naught cross g, the middle finger would be in towards you. Okay, out here, g cross v naught. Okay, g cross v naught, g cross v naught. The middle finger would be away from it or towards or outside the screen, isn't it? So this is positive k plus k. So this much is understood. Okay, I got the value of angular momentum at any point in time. Fine. Now see, if I just multiply them, okay, out here, V naught T into GT. What is V naught T into GT? V naught into GT square. So this would be V naught into GT square. V naught into GT square. Out here, half GT square into V naught. What would be the term? V naught into GT square by 2. So V naught GT square by 2. Okay, and this is minus k, this is minus k, this is plus k. Okay, now can I shift this minus out here? Of course I can. So I'm shifting this minus out here at the front. Okay, so our resultant is minus v naught gt square sine 90 plus alpha k plus v naught gt square by 2 sine 90 plus alpha positive k. Okay, since these vectors or both the vectors are in same direction, can I directly subtract them? One is towards plus k, one is towards minus k. Okay, so I can directly subtract them. No, so v naught gt square by 2 minus v naught gt square. So angular momentum. is equals to m into minus v naught gt square into k. So this is the value of our angular momentum. Understood? Sorry, minus v naught g square by 2. See, this term minus this term would be nothing but minus v naught g square t, sorry, minus v naught g t square by 2, isn't it? Okay. So my net angular momentum is nothing but mass into this value, and the direction of angular momentum is negative of k. That means in this direction. Okay. Even if you apply logic, okay, at any point, okay, at any point, see, if you do first vector r, second vector cross v, okay, let's say at point or at highest point in that first vector, second vector, the resultant vector is towards negative z axis, no? So at any point in the projectile, the resultant vector would always be, or the angular momentum would always be towards you. Okay. Till you use your right hand, everything is fair and fine. In your entire physics, you only have to use your right hand. Okay. So this was the first part of the problem that I obtained. Understood? Now let's move on to the next question. Now before learning this question, or before solving this question, we have to learn a little bit of theory. Okay. And the name of the theory is angular momentum. Angular momentum of a particle moving in a straight line. Moving in a straight line about moving in a straight line with constant velocity. Moving in a straight line with constant velocity. Constant velocity about any origin. Oh, about any origin. Any origin. Okay. So what we are going to study is angular momentum of a particle moving in a straight line with constant velocity about any origin. So that means if there is a particle, okay, and this particle is moving in a straight line, that means this is the path of the particle. Okay, and this particle is moving with constant velocity. I have to find out the angular momentum about this point or about this origin. Okay. So what I'll be trying to prove out here is doesn't matter in which position the particle is. Okay, at which point the particle is. Okay, if the particle is moving with constant velocity, the angular momentum of this particle about any origin, let's say this origin, okay, will always be constant throughout the path of the particle. That is what I'm trying to prove. Okay, so before trying to prove or before our proof, let's understand one concept which will be very important. That concept is, see, suppose this is a vector and b vector. Okay, the angle between them is theta. Okay, now suppose I'm doing a dot b, okay, or magnitude of a into magnitude of b into cos theta. Okay, and a cross b was nothing but magnitude of a into magnitude of b into sin theta. What I'm trying to learn out here is how we take the component of cos theta and sin theta. Okay, so while taking component or while doing a dot b, I can do two things: either draw a straight line, okay, and take the component of b along a, okay, or I can draw a straight line out here, or suppose this was a, this was b, okay, or I can draw a straight line out here, okay, and take the component of a along b. That means this a dot b is nothing but a into b cos theta, or component of b along this line, isn't it? Which is same as b into a cos theta, okay, or b into component of a along this line. Okay, this was the basic principle of dot product. Now for cross product, okay, what we have to do is the same thing, but it a little bit of twist. Okay, the twist out here is draw a perpendicular. Okay, that means line perpendicular to a is this line. Okay, line perpendicular to b is this line, isn't it? Okay, so it is nothing but a into component of b along this line. Okay, along this perpendicular line is nothing but ab sin theta. Vector a into component of b along this line is nothing but ab sin theta, or vector b, okay, into component of a along this line is nothing but ab sin theta. Understood? In dot product, you should draw a line and take component of vector along or component of b along this line or component of a along b. In cross product or while dealing with sin theta, you draw a perpendicular line to the first vector or perpendicular to the line of second vector. Okay, you draw perpendicular to first vector or perpendicular to second vector and take the component of other vector along that perpendicular line. Take the component of other vector along that perpendicular line. Understood? Okay, so this is the trick, or no, this is the observation that you must apply out here. Okay, so okay, so now this particle, okay, let's say of mass L, was moving with constant velocity along this line. Okay, now let's say at first position, at time at any time. Okay, since there is no acceleration, the velocity will be constant throughout the path. Let's say this is r1. Okay, this vector is r1. After some time, the particle reached out here. The particle reached out here. It is moving with same velocity, and this vector is r2. Okay, r2. What I'll be trying to prove out here is the angular momentum of this particle out here is equals to angular momentum of this particle out here about the point or about origin. Or r cross v, okay, is same as r2 cross v out here. r1 cross v is equals to r2 cross v. Okay, that is the thing that I'm trying to prove out here. Okay, now let's say r1 cross v is what? Magnitude of r1 into magnitude of v into sine of angle between r1 and v. Let's say that to be theta 1. Okay, r2 cross v is what? Magnitude of r2 into magnitude of v into sine of angle between r2 and v. Let's say that to be theta 2. Okay. Okay. So let's say this point at A, this point at B. Okay. Angular momentum at A. Angular momentum at A is nothing but m, okay, into r1 cross v. Okay. Or I can say this as m into magnitude of r1 into magnitude of v into sine of theta 1. But theta 1 is the angle between v and r1. Okay. Okay. Now, if I just do this thing, or if I just rearrange this variables, okay, r into v1 or r1 into v, I'm just interchanging the position, magnitude of v into r1, or this is nothing but m into v into r1 sine theta 1. Okay, r1 sine theta 1. Okay. Now, if I want to find the component, or if I want to find out the value of r1 sine theta 1, what do I do? I draw a line perpendicular to velocity v. Okay, this is line perpendicular to velocity v. Okay, and take the component of r1. Okay, sorry, this line is parallel to v. This line is perpendicular to v. Okay, this line is perpendicular to v. This line is perpendicular to v. Okay, when teachers make mistake, this line is parallel to v, no, and this line, okay, these lines are perpendicular to v. Okay, so what I'm trying to say is, okay, I'll be just using one perpendicular. Okay, this perpendicular. I'm not using this line and this line. It will be very confusing. Okay. So I have to take the component of r1. I have to take the component of r1 along this perpendicular line. Okay, that is nothing but r1 sine theta 1. r1 sine theta 1 is nothing but component of r1 along this perpendicular line. Sir, how do we do that? Okay, let's see another way. Okay, if this is theta 1, this angle is also theta 1, no? This angle is also theta 1. And if this angle is theta 1, this angle is 90, this is nothing but theta or 90 minus theta 1. So r1 cross, r1 into cos 90 minus theta 1 is nothing but component of r1 along this line. Okay, so r1 cos 90 minus theta 1 is what? r1 sin theta 1, isn't it? So this is nothing but r1 sin theta 1. Okay, so this length is nothing but r1 sin theta 1. r1 sin theta 1. So I'll get my value of mg r1 sin theta 1. Okay, now let's take this value b. Okay, at position b. At position b, what is the angular momentum of the particle about origin? It is nothing but am into r2 cross v. Okay, or am into r2 vector into v vector into sine theta 2. Where sine theta 2 is nothing but the angle between r2 and v. Okay, see, and if I rearrange this term v and r2, it will be nothing but am into v into r2 sine theta 2. Okay, now similarly if you check, no, the value of r2 sine theta 2 would be same exact this line or this much line. See, if this is theta 2, this would be theta 2, this would be 90 minus theta 2, and r2 cos 90 minus theta 2 is nothing but this much length only. So this length is also is equals to r2 sine theta 2. Understood? So if I say angular momentum, okay, at point A, angular momentum at point A is nothing but m into magnitude of m into magnitude of v into this much length, isn't it? Which is equals to angular momentum out here. Why? Magnitude of m and the value of velocity remains constant into r2 sine theta 2 is nothing but the same exact length. Okay. So the angular momentum of a particle moving in a straight line with constant velocity, okay, is same or throughout its path, okay, at any point or at any through any origin. Understood? And what is the direction of angular momentum? Just apply right hand rule. Okay. What is the first vector? r1. Okay. What is the second vector? V. So r1 is in up direction. See, r1 is in up direction. Position vector r1. V is in same direction. So if you curl your right hand, the thumb gives the direction towards you. Okay. So this is the direction of angular velocity. For the second, r2 is in this direction, v is in this direction. Okay. the direction of angular momentum would be in this direction. Suppose the particle was out here, okay, in negative x, okay, it would be the same direction. Angular momentum wouldn't change. R vector, v vector, okay, R vector was in this direction, okay, and v vector was in this direction. So R vector cross v, it would be same. The direction of angular momentum would be same, and the magnitude of angular momentum would also be same. Okay, the momentum of any particle moving in a straight line is nothing but mass of the particle into velocity of the particle into component of r perpendicular to the line of v. Okay, understood? Okay, and this theorem or this technique is valid for any cross product. You'll learn this technique better in torque or calculation of torque from r cross f. Okay, sometimes you have to take the perpendicular to torque, sometimes you have to take perpendicular to velocity. Okay, but out here I want you to remember the angular momentum of any particle moving in a straight line is constant throughout its path, and that value is nothing but mass into velocity into component of r perpendicular to the velocity vector. Okay, now we'll learn this, or now we'll see this problem. Okay, in this problem there is a carom board. Okay, this is a carom board. This is one of the particle, and this is the wall of the carom board. Okay, this is the wall of the carom board, and I'm looking at this carom board from the top. Okay, now somehow this particle, okay, struck the wall and rebounded in this direction. Okay, so in your elementary mechanics or in your elementary things, you did said or you did that if the velocity out here is v, okay, if the velocity out here is v, the velocity after rebound would also be v, no? Okay, and one more observation. Okay, see, just observation that is connected to collision. Okay, so whenever collision is there, all I said was apply conservation of momentum, conservation of kinetic energy, and conservation of not conservation coefficient of restitution. But out here, can we apply conservation of momentum? Look properly, the momentum would change its sign, no? Isn't it? Now I told you one more thing about seeing the entire collision from the frame of reference of center of mass. Okay, and that is actually the generalized way of dealing with collision. See, if you see this entire collision, no, from the frame of reference of center of mass, the mass of this particle is n, the mass of this wall is infinity. So the center of mass would be in this wall only, isn't it? Okay. Now what did I say? A particle will rebound and change its velocity with the same magnitude. See, that is exactly what is happening. In y direction, there is no collision or there is no change in velocity. Okay. In x direction, the velocity will reverse in direction with the same magnitude. That means the initial velocity vector is vi, okay, vi cap or vx plus vy. The final velocity would be minus vx plus vy. Okay, that means the y component of velocity will change, the x component of velocity would get reversed. Okay, now let's come back to the rotational part of the problem. Okay, in rotational part of the problem, the question is asking this particle collided out here and rebounded. Okay, I have to find a point in space through which the angular momentum out here before collision and angular momentum after collision is same. Okay, doesn't change. Okay, now see, if I take any point in space, okay, any point in space, the angular momentum throughout this path about that point would be zero. Okay, so let's take this point in space. Okay, what is the angular momentum about this origin? Let's say particle is out here, particle changed out here. This is nothing but v into this much length, isn't it? V into this much length. Okay, so angular momentum of this particle throughout this path would be mass of this particle into v into this much length, and this length is nothing but perpendicular to this what velocity vector. Fair and fine. But after rebounding, the magnitude of angular momentum, see, is nothing but v into this much length. Okay, v into this much length. Let this be L1, let this be L2. Okay, so magnitude of angular momentum throughout this entire path would be v into L1 or m into v into L1. Okay, and the direction would be L1 into v towards this. While we're coming back or while rebounding, the direction of angular momentum would be v into L2 into v, would be in the same direction. So the direction of angular momentum is same, but is the magnitude of angular momentum before collision and after collision same? No. So I have to find a point in space, or I have to find a point in space through which the angular momentum before collision and angular momentum after collision is same. See, before collision and after collision, the direction of angular momentum will be same. R1 cross v, okay, R2 cross v, okay, both are towards zero. I have to find out at which point and at which origin is the magnitude of angular momentum same. Okay, so if I take, now let's say, okay, see the trick I'm applying. This is a straight line. Okay, now if I take my origin at any point in this line, okay, at any point in this line, see what will happen. Magnitude of angular momentum before rebound is nothing but v, sorry, this length or perpendicular to v, L1 into v, okay, and magnitude of angular momentum after collision will be nothing but this angle or this much length, L2 into v. Okay, now see, by symmetry, can I say L1 is equals to L2? Okay, by symmetry, can I say L1 is equals to L2? So if L1 is equals to L2, the magnitude of angular momentum before collision and the magnitude of angular momentum after collision would be the same value, no? This is angle alpha. Okay, similar triangles. Understood? So if you take the origin at any point out here in this midpoint, the angular momentum before collision and after collision would remain same. Understood? Now the second part of the question is asking what is the angular momentum or what is the change in angular momentum about this point O dash. Okay. So what is change in angular momentum? Final angular momentum minus initial angular momentum. So the first part of the question is solved. If I take my origin at any point along this line, the angular momentum before collision and after collision would be same. Now the second part of the question is my origin is out here. Okay, this is my origin. Okay, if this is my origin, what is final angular momentum minus initial angular momentum? This is final angular momentum minus initial angular momentum. So second part of the question, see, final angular momentum is nothing but if I draw perpendicular to V or if I draw a line, this is parallel to V. Okay, this line is perpendicular to V, connecting the origin. Okay, and before angular momentum, this is origin. Okay, this is the extension of initial velocity vector, and this line is perpendicular to initial velocity vector. So this line is L1, this line is L2. Okay, about this point. Fair and fine. Now if you observe properly, okay, L1 or L2 cross V, see, L2 cross V is in this direction. Okay, whereas L1 cross V is towards V. Okay, the magnitude by symmetry, the magnitude of both the angular momentum will be same. Okay, because L1 is equals to L2. Okay, but observe the direction out here. L2, okay, cross V is towards you. L1 cross V is away from you. Okay, understood? So the direction of angular momentum before collision and after collision are opposite, no? Okay, what was the first step? The first step was draw a perpendicular line to the velocity. Okay, and join origin to that perpendicular line, or draw a perpendicular line to velocity connecting the origin. Okay, draw a perpendicular line to the velocity vector connecting the origin. Okay, this was the technique that I taught you in this previous slide. Okay, so in this, if I take this as origin, the magnitude of angular momentum is same, but the direction of angular momentum is different. Okay, so if I say change in angular momentum is nothing but final angular momentum vector minus initial angular momentum vector. And what is final angular momentum vector? See, if you consider this direction as negative z-axis, this direction should be positive z-axis, isn't it? So the direction or magnitude of final angular momentum is nothing but L1 cross V, okay, towards you or towards positive. So L1 into V into L1 into V into positive K. Okay, the magnitude of initial angular momentum is nothing but L2 into V. Okay, minus of L2 into V into negative K. Why negative K? Because the direction of this angular momentum, okay, before collision is towards you. Okay, so fine. By symmetry, I can say that the magnitude of L1 is equal to the magnitude of L2, isn't it? So the magnitude of L1 is equal to magnitude of L2. So I can substitute this by also L1. Can I take this negative outside? If I take this negative outside, it will become positive. So I'm taking this negative outside, it becomes positive. So the change in angular momentum is nothing but 2 into L1 V into K. Okay, so final angular momentum minus initial angular momentum is equals to twice of L1 into V. But L1 is the perpendicular line or length of perpendicular line from V vector to joining the origin. Understood? Okay, so this was our question. Okay, so this question is about conical pendulum. Okay, so before starting or before understanding about conical pendulum, let's understand what happens in conical pendulum. Okay, so there is a string attached to a mass. Okay, and this mass, instead of moving like this or like this, it will rotate in a circle. Okay, this will rotate in a circle, and this kind of pendulums are called conical pendulum. Okay, this will rotate in a circle. Okay, this is the orbit of the pendulum, and this type of setups are called conical pendulum. Fair and fine. Okay. So before analyzing this pendulum, okay, there is one thing I would like you to do. See, in this pendulum, mg force is acting downward. Okay, and that mg force is balanced by the upward or vertical component of tension force. No, and why is that? Is this particle moving up or down? No, this particle is only rotating in a circle. No, this particle is only rotating in a circle. So the vertical component of force is equals to 0. So T or vertical component of tension force is balanced out by the mg force. Okay, so there is only one force in this pendulum, and that is the centripetal force. So this is the orbit of the ball. Okay, and this is the ball, and there is only one force acting, that is the centripetal force. That means the component of tension force along the centripetal direction or along the radial direction. Okay, so centripetal force. Now see, in this conical pendulum, okay, a ball is moving with a circular orbit with the help of a centripetal force, isn't it? When the ball is out here, the centripetal force would be inward. When the ball is out here, the centripetal force would be lesser direction. Okay, so conical pendulum is nothing but a simple case of a ball or a bob moving in a circular orbit or moving in a horizontal circular orbit. That much is fair and fine. What this question is asking is that find the point in space through which the angular momentum of the ball would be zero. Okay, that means what? This ball is moving at a constant velocity in the circular orbit. No? Okay, so let's take a point out here. The velocity of the ball would be towards you, isn't it? The velocity vector of this ball would be towards you. Okay, in this direction. Similarly, in this diagram, the velocity of the ball would be towards you. This is the velocity of the ball. Okay, the velocity of the ball out here would be towards right. The velocity of the ball out here would be inwards. The velocity of the ball out here would be towards left. Okay, so this ball is moving in a circular orbit, a horizontal circular orbit. Fair and fine. Now to find a point in space through which the angular momentum of this ball always remains constant. Okay, that means what? That means suppose I'm taking an origin out here. Okay, this is my origin or a point in space. Okay, what is the formula for angular momentum vector? The formula for angular momentum vector was what? L, angular momentum is equal to r cross p or m into r cross v. This we have already done. So the formula for angular momentum is equals to L is equals to, or L vector is equals to m into r cross v. Where v is the linear velocity, r is the position vector from the origin. So if I take my point in space out here, what is the position vector? Position vector is nothing but this line connecting the bob and the origin, isn't it? So this is my position vector. Okay. Now see what happens if I take the origin out here. Okay. Angular momentum is equals to r cross v. That means first vector r, second vector v, angular momentum vector middle finger. So r, okay, r cross v. The value of angular momentum would be in this direction, isn't it? The value of angular momentum would be in this direction, perpendicular to both v and r. Okay. And as this ball rotates, okay, as the ball rotates with constant velocity, see, when the ball arrives out here, the angular momentum would be in this direction. When the ball arrives out here, the angular momentum would be in this direction. When the ball goes towards the back, the angular momentum would be in this direction, isn't it? So as the ball rotates, the value of angular momentum or the direction of angular momentum changes. Okay, somewhat like this. See, out here the angular momentum is in this direction. So when the ball rotates, the angular momentum will change, or the vector of angular momentum will change somewhat like this. Okay. Okay. So even though the magnitude of angular momentum is constant, the direction of angular momentum is changing. No? So I have to select a point where both the magnitude and the direction of angular momentum remain constant. Okay. So let's say I select my origin out here. Let's say I select my origin out here. I select my point out here. This is the orbit. This is the ball. Okay. My origin is out here. Or this is my origin in space. Now if you check, the velocity out here is equals to v. The radius vector out here is equals to r. Okay. So r cross v. Okay. R cross v. The angular momentum would be always upward. Okay. And doesn't matter in which position of the circular orbit the particle is. The value of angular momentum vector would always be upward. Check if you take your origin. Okay. R cross v. It is upward. Out here when the particle is out here. R cross v. Okay. The value of angular momentum is upward. When the particle is out here. Okay. R cross v. Okay. The angular momentum is upward. So it doesn't matter in which part of the circular orbit the particle is. The direction of angular momentum will always be upward, isn't it? And the magnitude of angular momentum is r into v. And in a circular orbit, the magnitude of r is always constant and velocity is always constant for a conical pendulum. So if I take my point in the center of the circle, okay, the magnitude of angular momentum will always remain, magnitude and direction both will always remain constant. Understood? Now what happened when you take your angular momentum, let's out here? The same case will happen out here. If you take the point outside the circle, what would happen is both the value of r would change when it is moving in a circle. Okay, so the magnitude and direction both will change in when you take a point outside the circle. Okay, there is one more way of understanding this problem. Okay, see, we know that L is equals to r cross v. Okay, so when you do that, okay, r cross v, that means r vector v vector, and this is angular momentum vector. So angular momentum vector must not change in direction or in magnitude. Okay, to change the angular momentum vector either in direction or in magnitude, A torque is needed, isn't it? To change the velocity vector and magnitude, a force is needed. See, in circular motion, what is to happen? The velocity vector is to change in direction. No, the magnitude of velocity vector was constant. To change the direction of that velocity vector, a force was needed, and that force was called centripetal force. Okay. Similarly, out here, to change the direction of angular velocity, okay, or to change the direction of angular momentum, okay, even if the magnitude of angular momentum is constant, just to change the direction of angular momentum, some torque should be needed. Later we'll learn that that torque is called gyroscopic torque that I taught you in kinematics before. Okay, see the lectures of kinematics, it will be very helpful. Okay, so to change the direction of angular momentum, a torque is needed, and that kind of torque is called gyroscopic torque. Okay, so I must select a point in space where both where any type of torque is equals to zero. That means neither the angular momentum will change, neither the magnitude of angular momentum will change, neither the direction of angular momentum will change. That means my net torque or any kind of torque, okay, on this circular orbit should be equals to zero. And what is torque? Torque is nothing but R cross F. See, torque is nothing but R cross F, isn't it? See the value. Out here, torque is nothing but R cross F. Okay. So my value of R cross F out here should be equals to 0. Okay. Now if you see this diagram, what is the direction of centripetal force? In this direction. What is the direction of R? In this direction. So the angle between R and F is always 180. No? So if I do this one, torque or magnitude of torque is equals to magnitude of R into magnitude of F into sine theta, where theta is the angle between R and F. So if you take the point origin of it, the angle between R and centripetal force would always be 180, and sine of 180 is nothing but 0. Same thing happens out here. Okay, the angle between R and centripetal force will be 180. Same thing happens at every point in the circular orbit. Okay, now you might ask, sir, if I draw a straight line, okay, any point in this straight line, the angle between R and F would be equal to 0. Okay, that's fair and fine. But as the ball comes out here, you have to change that point also, no? See, if you take the center, what happens is the angle between R and F is always 0. Okay, but let's I take my point out here. Okay, so in this position, the angle between R and F is equals to 0. But when it comes out here or at in front of you, when the ball is moving in this direction, then going in this direction, then backward. So when the ball comes out here, the value of R would be this one, whereas the value of F would be in the centripetal direction, and the angle between R and F would not be equals to 0. So the only point where the net torque is equals to 0 is at the center of the circle. Okay, and the direction of angular momentum is upward if the velocity of the particle is constant. So this question is fair and simple, this manner. Okay.